Now we can talk about Boyle's law. Boyle was looking at the relationship between pressure and volume, and he did these experiments at home. And he had this J-shaped tube full of mercury. So he'd have this fill this up with mercury, and he noticed that when he increased the pressure by increasing the amount of mercury in there, that the volume decreased. And so if you put some more mercury in here, it gets really small, so the volume decreases. So he said if you increase the pressure, you're going to decrease the volume, as long as you don't change the temperature. That's true. And that became Boyle's law, and that's what you can see over here in this graph. If you start off with high pressure, as you decrease the pressure, the volume is going to increase. So increasing pressure and decreasing volume. So pressure times volume is equal to some kind of constant. And so if you summarize that, you get P1 V1 equals P2 V2. And so that's Boyle's law, and that's what we are going to use in this next problem. All right, so you have a gas in a flexible container. Initially, the pressure is 729 torr. So that's your initial pressure, 729 torr. And the volume, initial volume is 0.933 liters. 0.993 liters. And the temperature gets kept constant. The volume is reduced. So the volume is going down to 0.720 liters. So what do you think should happen to the pressure if they're inversely proportional? If you decrease the volume, you should increase the pressure. So that's what we're going to calculate. So we're going to use Boyle's law. P1 V1 equals P2 V2. Plug that in and solve for P2. These are second sets. So P1, 729 times V1, 0.993. And I'll put the units in, that's liter, and this guy's torr, equals P2 times 0.720 liters. So to solve for that, for P2, we're just going to divide by 0.720 liters. Divide over here by 0.720 liters. Your liters are going to cancel, and you're going to end up with a P2 of 1005.41 torr. And we're going to want 3 sig figs, so we had 3 sig figs in this pressure, 3 in both of the volumes, so we want 3 here. So we're going to rewrite this in scientific notation. 1.01 times 10 to the 3, so I went 1, 2, 3, so I rounded this 5, I rounded the 0 up to 1 because this was a 5, and then don't forget your units. So we have 1.01 times 10 to the 3 torr. Alright, here's another one. So we have a gas sample occupies 5.24 liters at 776 torr. So we have our V1, it's 5.24 liters. Our P1, 776 torr. Find the volume. What's our volume going to be when the pressure is increased? So now we're increasing the pressure to 556 torr. So we would expect the volume to go down. So we have P1, 776 torr, times V1, 5.24 liters, equals P2, 856 torr, times V2. So divide by 856 torr, divide by 856 torr, and our answer should be in liters, so torrs are going to cancel. So you're going to do 776 times 5.24 divided by 8.56. So you can pause the video for a second and work that out in your calculator, and you get 4.75 liters. So that's with three sig figs here. This video down here, this YouTube, you can click on that link, and this will show you some visual representation. Just a video on some of these laws. I can't remember if that one's Boyle's or if it's Charles' law. Lost our place. Alright, so the combined gas law is going to be important too. So if you remember what Charles' law, Charles was talking about volume over temperature and how that's equal to a constant. So V over T equals V over T. And Boyle said that PV pressure times volume equals a constant, but P1 V1 equals P2 V2. So if you put all this together, you get something called the combined gas law, and that says PV over T equals PV over T. So P1 V1 over T1 equals P2 V2 over T2. And this is the combined gas law, which is great because it gets you all of the relationships. So if temperature is staying constant, then just ignore temperature and you get P1 V1 equals P2 V2. That means like if T1 is the same as T2. Or if your pressure is being held constant, then ignore the pressures, right? Just scribble out those, right? Forget pressure, right? And then you get V over T equals V over T. So the combined gas law, you can get all the gas laws from the combined gas law. So you can get Charles and get Boyle from there. But so we have PV over T equals PV over T. So PV over T equals the constant. PV over T has to equal that. A lot of times when we're looking at the combined gas law or just gas laws in general, they'll tell you that the reaction, one set of conditions takes place at standard temperature and pressure, or STP. STP just means they're telling you the temperature and they're telling you the pressure. The temperature is 0 degrees Celsius, or add 273 to that, so 273 Kelvin, and 1 bar, which is about equal to 1 atmosphere. So we're just going to use atmospheres. So the standard temperature and pressure, whenever you see that in a problem, it really means that the temperature is 273 Kelvin and the pressure is 1 atmosphere. So let's see if we can use this in another problem, and using the combined gas law. So what is the STP volume? So when the temperature at STP that's 273 Kelvin, and the pressure is 1 atm, and they want to know what's the volume at STP. So what is that volume? If a gas initially has a volume of 729 milliliters and a temperature of 44 degrees Celsius, but we don't like Celsius, so we're just going to add 273 to that. And what do we get when we add 273? It's 44. Then in your calculator you get 317 Kelvin. 317 Kelvin. And your pressure is 881 millimeters of mercury. Now, be careful, because our units don't match here. So Kelvin matches Kelvin, that's good. But ATM and millimeters of mercury are not the same thing. So we want to, if we convert this, it doesn't matter which one you convert. I think it's just easier to go from ATM to millimeters of mercury, because 1 atmosphere is 760 millimeters of mercury. So you end up with 760 millimeters of mercury as your pressure there. So these are actually your initial, they tell you, these are your initial conditions here, and you're looking for volume 2. But again, it doesn't matter what you call 1 and 2, just as long as this temperature and this pressure and this volume go together, and this temperature, pressure, and volume go together. But it doesn't, this subscript really doesn't matter. So P1 V1 over T1, let's see, we have 881 millimeters of mercury, P times V, 729 milliliters, divided by 317. So the only unit that really is set is Kelvin. Temperature has to be in Kelvin or this is not going to work. Volume doesn't matter if it's milliliters or liters, but if this is in milliliters, then this is going to be in milliliters. If this one was in liters, then this one's going to be in liters. And your pressure, as long as they match, it doesn't matter what it is. So it could be atmospheres. You could have just as easily put millimeters of mercury over here into atmospheres. Either way, you should get the same answer. So P2 is 760 millimeters of mercury times V2, that's what we're looking for, over T2 here, 273. Alright, so you have to solve for volume. So what I would do first is multiply. You can get a number here. You can do 881 times 729 divided by 317. You can get a number there. And then multiply that number by 273. So we're going to cancel your multiply over here by 273. Alright, and then I want to divide this number by, I'm trying to solve for V2, so I want to divide this number here by 760. Divide both sides by 760. Alright, so in your calculator, you can do 273 times 881 times 729, get a number, and then 760 times 317, get a number, and then do the top number minus the bottom number, and that's how you can get V2. So V2 ends up being Where's my volume 2? 728 milliliters. 728 milliliters. So work that out and make sure you get the same number.